All right, go. So, let me start off with a question. Why do we care about points of intersection? Anybody?
Tells you where to plot the graph.
It can tell us something like that, yeah. What else might it tell us? What do y'all at home think? Why do we care about points of intersection? What might they tell us? You're correct. Silence is the right answer. Yes, sir.
It gives you your X and Y's.
Yeah, it can do something like that, right? Like it tells us something about just this, where our graph intersects. But depending upon what our graphs represent, they can tell us something about our systems of equations, right? So for example, how many of y'all are business majors? The majority of us. What about the two of y'all that didn't raise your hands? What are y'all majoring in?
I don't know.
You don't know?
Sport management.
Sports management? Awesome. All right, so one thing they can tell us for the business majors in here is something about supply and demand, right? Let's say we're looking at cost and revenue of making a commodity good. If we know where those two equations intersect, then we know where we break even, right? Because if cost all of a sudden becomes equal to the revenue, well, then we're breaking even from that point on. And now we know how to mark up our product. Make sense what I mean? Yeah. So as an example of this, let's look at that last example we were talking about last class. We've got these two commodities, or this one commodity that we're making. It costs us 65 cents to make. And there's an initial investment cost of $10,000. So you want to start your tech company, you got to build the factory, right? That's where this initial $10,000 investment starts off. And then every time you make your microchip or whatever it might be, it costs you 65 cents. That's what this is saying. Now, you sell that then at $1.20 for every chip, right? The question here is, when do you break even? Well, you're going to break even when the function, the equation representing cost and the equation representing revenue are balanced, right? When they're equal. Everybody with me on this? So in that way, one thing it might tell us is, well, when our break-even point occurs. Obviously, in this example, everything below that point, you're going to lose money. And everything above that point, you're going to make money. So, just like we did in last class, we set these two equations equal. We solve for x. And then if we want to know what y is, well, then we're going to plug this x back into either of these equations. Make sense what I mean? Yep. No. So having said that, let's talk about the supply curve really quick. Business majors, what do you all know about the supply curve? All right, what do you know about supply side economics? I'm loving it, sweet. All right,
I
so.
took it and failed the class.
Say what?
I said I took it and failed the class. That's what I meant.
Well, let's see if we can fill in some holes here then. So what the supply curve is telling us is it's the relationship between the unit price of a good and the quantity of that good, right? Similarly, sorry, I had something backwards in my head for a second. Similarly, we have the demand curve, which is the opposite, right? So the demand curve is a relationship between the number of goods and the price, as is the supply curve. The supply curve looks at it from the business perspective, right? If I have a whole bunch of these goods, I want to sell them at a high price because I need to make money off of them. The longer they sit, the more expensive it is to make them for me, so they must cost more in my mind. The demand curve is from our perspective, right? So let's think about it as us going to Walmart, or to McDonald's. Let's say we buy 4 McDoubles. All right, that first McDouble, we're good with it, right? Second McDouble, we're getting full now. Third McDouble, this was a bad idea. Fourth McDouble, hey babe, you can have this, right? Like that's what this idea is. Because as we eat in more of these McDoubles, they depreciate in value. They're no longer satisfying a need that we have. This is what the supply and demand curves tell us. Now, there's a question that naturally arises when talking about these. What's the best number of goods to make? When is our system optimized? And the solution to this is to find the equilibrium point. The equilibrium point is when your demand and your supply are equal. That's all it is. So in this way, another use for setting equations equal is to find equilibrium points when talking about supply side economics. For whatever it's worth, looking around, none of y'all are going to remember this, but somewhere like, I think it was 01, 02, PlayStation intentionally underproduced PlayStation 2s so that the price would go through the roof. That way they could increase the actual value of it on the market, because there was more demand than there were devices. And the way they were able to do that was by looking at the supply side economics of what was going on. So to kind of motivate why you would care about this, because let's be honest, how many of y'all are like, it's just math, where am I going to use it? Like, out of curiosity, how many of y'all have thought that? Right, like, you're not going to hurt my feelings if you say it, because yeah, it's just math. Where are you going to use it? Like, it's abstract. It's something we do on paper. They forced me to go through these classes in college. I don't know why though. The reason why is for things like this. Things like what PlayStation did, where they were able to use supply side economics and setting equations equal to each other to find out how to produce commodity goods to increase your profit margins. Make sense what I mean? Everybody with this? Cool. So, using these two definitions, we got an equation representing demand for DVD players and another equation representing supply. So we want to know with these two equations what the equilibrium point is, what the fair market price and commodity numbers are for these DVD players. So what we're looking for is going to be this center point, right? This point of intersection. Everybody at home, don't worry, I'm going to start using the board in a second here. So what this is going to look like, we're going to set these two equations equal to each other, right? When we set them equal, we're going to solve for x, just like we did with that other problem. Once we solve for x, then we're going to plug that value back into either of our equations and solve for y. That'll tell us both the number of goods, the number of DVD players we should sell, as well as the value we should sell it at. Make sense what I mean? So, for those of y'all at home, what this looks like, we've got our first equation for demand. Which is our price is equal to, what is that, 195 minus 5.8x, and our supply is 150 plus 3.2x, right? Go. So like I said, we're going to set these equal to each other. Setting them equal, we're going to find that cool 195 minus 5.8 x is equal to 150 plus 3.2 x. From here, we're going to push and pull. We're going to rearrange terms. First thing we're going to want to do is add this 5.8x to both sides. Make sense what I mean? And then we're going to want to move this 150 to the other side. So we're going to subtract it from both sides. Yeah? So what this is going to look like is going to be 195 is equal to 150 plus 5.2x plus 3.8x. Add that backwards. 5.8 plus 3.2x, which is going to be equal to 150 plus 9x. Then we're going to want to subtract the 150 from both sides. To get 45 is equal to 9x. Which tells us when we divide 9 from both sides, tells us that x is equal to 5, right? This is the process. This is all it really means to set equations equal and solve them. When we're trying to find these intersection points, it's just when are they the same thing? When is equation 1 the same as equation 2? The end. Everybody cool? So I'm going to skip over mathematical models. I just want to bring your attention really quick to a collection of graphs that's titled types of models. These are going to be exactly what it sounds like. Different types of common models that show up all over the place. These are good things for y'all to get used to recognize. For example, cubic model. Generally, anytime you have a polynomial of degree 3, it's going to look something like this cubic model. And the same is true for all of these, right? Anytime you have a linear model, it's going to be a line. A quadratic model, it's going to be a parabola, so forth and so on. So these are something good for y'all to get to a point where you can recognize, because they're going to show up a lot, right? Cool. All right, section 1.3. And slope. What can you all tell me about slope? Like, functionally, what does it mean? What does it represent? Rise over run, okay? So, what does that tell us? Like,
Whether it goes up or down.
say what?
Whether it goes up or down.
Yeah, it tells us the direction that our line is tilted, as well as how tilted our line is, right? Now, let me ask a question. This is going to show up later in the semester. Let's say we have an equation like this. Can we associate a slope with it? What do y'all think? Kind of. Not with a single point, but with what's called a secant line that goes through 2 points. Now, I point this out because, like I said, later in the semester, we're going to talk about the derivative. And generally speaking, the derivative is thought of as a representation of slope, but there's a little bit more to it than that. So I just kind of wanted to bring up this comparison while we're talking about slope. That this thing can't actually have a slope. Makes sense what I mean? Because it's not a straight line. So slope only makes sense in the context of straight lines. So, having said that, slope, as already stated, is the measurement of how steep a line is. And B is the y value, is the y value, yeah, associated with our y-intercept. Everybody cool with that? Let me go ahead and draw that in. So we've got this equation, it's a line, and the equation is written in the form mx plus b. B is our y-intercept, and m is our slope. M is equal to the change in y over the change in x. So again, it's the ratio of how much we change in the x direction to how much we change in the y direction. Everybody cool with this? Yep. Having said that, voila, slope-intercept form of the equation of a line, y is equal to mx plus b, where m is equal to the change in our rise, the change in our slope, our run. So how much we go up compared to how much we go over, and then again, that intercept. Having said that, the question might come up, well, can you all at home see this part of the board?
Yeah.
Oh, dope. Okay. So, the question might come up, what's the slope of that line? Of the vertical line? Doesn't have one. Doesn't make sense to measure it. Like, it doesn't have a number associated with it. And the reason why is because the x value isn't changing, right? So to say it had slope would mean we could divide by 0, but we can't. Agreed? So we say that vertical lines have undefined slope for this reason. Yeah. right, so really quickly, I'm gonna let y'all on your own try to solve C really quick. For those of y'all at home, I want y'all to try to solve this equation. To sketch it, to graph it. Sketch it / graph it, yeah. Anybody think they got it? You people? Which side of the graph is the highest side? The left is the highest side? How about y'all at home? What do y'all think? What's the highest side of the graph?
The left side?
Yeah, absolutely, right? Like what we've got is a negative sloped graph. How do we know that? We know that because we rearrange our equation to find that y is equal to 2 minus x, which is the same thing as saying 2 plus -1 times x. So our slope must be equal to -1. And knowing that, we can see that, yeah, our graph is going to look something like this. Everybody cool with this? Yep. So from this, another way we can think of it is, another way we can go about graphing these is say, all right, our equation tells us a bunch of information. It tells us that our graph is going to have to go through the point 0, 2. Let's go ahead and mark that. And from this, if we go over 1 unit, we're going to have to go down 1 unit, right? So another way of graphing these, by recognizing that the slope tells us quite a bit, right? So forth and so on. We can kind of do this iterative step method, right? We can go over 1 unit, go down 1 unit, go over 1 unit, go down 1 unit. And we get the graph of the slope. Make sense? Similarly, we can move to the left and then go up, right? Because what is this M measuring, this slope measuring? Again, it's measuring the change in how we move. If it's negative, then it means every right movement is going to be associated with a down movement, right? And every left movement is going to be associated with an up movement. Does this make sense? Yep. Cool. Awesome. So let's move on then. Some more slope. Already talked about that. All right, so one point that I want to make, I said that m is equal to the change in x over the change in y. I mean the change in y over the change in x. M is equal to delta y over delta x. Well, we know delta y is described or defined as y2 minus y1, right? Delta x, x2 minus x1. But does it really matter when we write out m? Does it matter if we use y minus 1 over, y1 minus y2 over x1 minus x2 versus y2 minus y1 over x2 minus x1?
No.
No, right? Because this would be the negative of that, right? Similarly, our numerators would be the negatives of each other. So those negatives would just cancel out. We come out to be the same answer. Everybody with me on this? So long as you keep your order the same when you're taking the difference, it's not going to matter. Everybody cool with this? Dope. All right. So what about this example 4 on slide? Which number is it? On slide 88. Let's see if y'all can do B really quick. What do y'all think the slope for that would be? Well, you are working on B. I'm going to do D. So what did y'all get for B?
I got 0/3.
0/3. Everybody else agree?
Yeah.
What does that look like? If you had to graph that, just knowing the slope, what would that look like?
Wouldn't it just be like straight line?
Horizontal.
Horizontal line. Yeah. So let's think about this. What's happening here? When we say that a slope is 0, we're saying that the y portion of it doesn't change, right? So if the y portion of it doesn't change, then it must just be the equation y is equal to some constant, which would look something like this. this example D, we're going to get an undefined slope. So it's going to be that exact opposite, right? It's going to be the line that's perpendicular to this. Everybody cool? Yeah. So looking at B, we can see if we were to plot just the points themselves, it makes a straight line, right? Straight horizontal line. And we can see by taking the difference, yeah, that change in y comes out to be 0. Which makes sense, right? Like, if y is not changing, then it's not going to move up or down. It's just going to move over. Yeah? Similarly, the example that I did, D, the slope comes out to be undefined. So the x doesn't change. Everybody cool with this? How about you all at home?
Yeah.
Cool. So this kind of antagonizes another natural question then. What if I know the slope and I know the points, or just one point? Can I derive another equation for the line? The answer to this is yes. Yeah, we can absolutely come back to or find another equation for the line. Knowing just the slope at one point, we can derive a new equation that would represent the line. For those at home, I'm going to write it on the board really quick. Minus 1, 1 is equal to m x minus x1. And we use this generally when we just have m and some points. Generally, when we're given just m and a point, we're going to use the point slope form, or when we're given 2 points. And the reason why is because if we're given 2 points, well, we can find m, right? And since we can find m and we know one of the points, we can now use point slope form. Everybody cool with this? So, having said this, check out this next example, example 5. We know that m is equal to 3. We know that x1, y1 is equal to 1, -2. We want to put this in point slope form. So we're just going to push and plug, right? Plug and play. What this is going to come out to be then is y minus -2 is equal to 3 times x minus 1. We can reduce all of this. We're going to get y plus 2 is equal to 3x minus 3. Everybody with me so far? Now let's move this 2 to the right. We get y is equal to 3x minus 5. So we started off with point slope form, and we were able to put it back into normal form, right? Yep. So really quickly, we can compare and contrast, right? We know that our equation is going through this intercept, which is where that 5 is coming from, and we know it has a slope of 3. So everything shakes out. Yep. So put it into point slope form, and we get into slope intercept form. And then not done anything different, right? Having said that, I'm going to skip over these. Now, for those of you at home, there is a slide. Let me see what page this is. Page 98. That's different equations of lines. I want you all to check it out and try your best to commit this in memory. Because I'm just not going to have time to write all of this out on the board, cover everything. What these different equations are different forms of writing the lines of equations, right? So you got your vertical line, your horizontal line, and then your 3 different forms. Having said that, let's say we have 2 lines, and we know they're perpendicular to each other. They both go through a point. So let's say we have this. Zero. Let's say this is the point 0, -2. We know, perhaps, that this line, from this we can get the slope of this line, right? Like using this setup, we can find the slope of line 1. We're going to use this information to find out everything we need to know about line 2. So start off with line 1 is perpendicular to line 2. That's what this little square means. We know line 1 goes through the points 2, 0, and 0, -2. So what this tells us then is that the slope is going to be 2 over 2, right? Everybody agree? Or just 1? So we know then that line 1 is the line formed by 1x minus 2. Everybody with me so far? How are we going to find the slope for line 2? Well, to find the slope for line 2, we need to know something. We need to know that when two lines are perpendicular to each other, their slopes are the negative reciprocals of each other. So this automatically tells us, since line 1 is perpendicular to line 2, and M1 is equal to 1, M1 is equal to negative 1 over M2, or just negative 1. Is everybody cool with this so far? Yeah. So from this, we now know that L2 at least has this point to 0. And a slope that's equal to negative 1. Yeah. Everybody at home still with me?
Yep.
Yep, cool. So because of this, we can now put line 2 into point slope form and find out what slope intercept form of line 2 is. Y minus 0 plus, my mistake, equals negative 1 times x minus 2. This is going to come out to be y is equal to negative x plus 2. And that's it. We just put line 2 into slope-intercept form. Line 2, putting it into slope-intercept form tells us something else. It tells us that this point is going to be the point 0, 2. Is everybody with me? Yeah? So why is this important? Well, it gives us ways of relating different graphs to each other, different equations. For example, here, we were just given two lines that are perpendicular to each other, that they share one point, and then the other one has an extra point. So really, we're just given like, what, 3 points of information? And from it, we were able to find out what both of the equations are. So why is this important? It's important because it allows us to pull a lot of information from very little. Make sense what I mean? Like, think about it, right? We took 3 points of information and discovered the equation that gave us solutions to a line that goes through an infinite number of points. And we didn't stop there. We found the equation for another line that goes through another infinite number of points. It's actually kind of dope if you think about it, right? Or I'm just a nerd.
Or we're not that smart yet.
That's the point of the class though, right? It's to get us all there on the same page. Personally, I love this shit. It's fucking dope as shit. I will bleep that out in the YouTube video. So, before we move on, I just want to summarize what it is I was just saying. In the event that we have a graph with two parallel lines, we say that line 1 is parallel to line 2, and their slopes are the same. Alternatively, if they are perpendicular to each other, we say that line 1 is perpendicular to line 2, and M1 is equal to -1 over M2. This is just for those of y'all at home who weren't able to see that slide. So having said that, I've already gone through an example. Let's keep carrying on. Actually, let's not, because it is time. So, have a good one, everybody. Do check out website. There's homework posted. If y'all have any questions, by all means, please feel free to shoot me an email. I promise things will start picking up soon. Have a good one. Those of y'all at home, do you have any questions?